Well, so in today's video, basically, I will discuss a few in my upcoming video. I'll discuss on motor uh, like circle diagram. But before that, we need to consider a generalized treatment. It's not totally generalized, but somewhat common between motor and generator. So that is the power flow. Here we will try to investigate power flow of synchronous machine. I will start my discussion with a generator, and then I will gradually move to motor also. For our ready reference, let me just quickly draw the generator phasor diagram that this is our V, E and E naught. I'm doing it for cylindrical rotor machine. This is IR, this is JIXL, JIXAS. Okay, so now let us draw the MMF. So it will be 90 degree with E, that will be FR. Then we will have our minus A, and then we will have our if not, that is making an angle 90 degree with this one. Right. So this is our phasor diagram. So with that, let us proceed. What I can write about this three-phase power is that it becomes boring using this white color. Let me write in sand. So in cylindrical rotor generator, if your terminal voltage is V and your current is I, then what we can write, the power output of the generator is electrical power is 3VI cos theta, where this angle is this is theta. So this is 3VI cos theta. What we can write, it is a dot product between V and phasor I. Now, what dot product means, what you studied in your vector means. Now, what is your PM? PM is the mechanical input. Now, how to find out that PM? Just let me check. Yeah. PM is equal to what? That will be PE plus. Here, I would like to mention one thing. Just because constant losses are like totally constant, including our coal loss, constant losses like including mechanical core loss, all these losses, they are pretty constant, so they actually give you kind of level shift, nothing else. So for this discussion I am considering this input. Obviously uh, input that is excluding the constant losses, excluding the constant losses that include, correct. So what I can write is this one is just like PE plus 3 I square R, where I square R is our variable loss in total 3 phases. It's creating trouble for my eyes. Let us back to that white. So what we can write from this phasor diagram is that if we consider this one is our phasor, like I'm taking a triangle, so this will be what, where IZS is our synchronous impedance, so we can write this is equal to 3 VI cos theta plus 3 IZS cos theta, right? I square ZS cos theta, because R can be replaced by ZS cos theta. No, wait a minute, not ZS cos theta. It is should be say uh, say it is gamma, where gamma is tan inverse xs by R. This angle is delta, this angle is theta. Well, now here, hold on a minute. So it is not cos theta, but what we can write, let us try to write it like 3 I square R. So from this, what I can write like 3 V dot I and 3 IZS dot I, right? So what is the phase of IZS and I? That is obviously, see, IR is lying in phase with I, but IZS is making an angle gamma with this, so it is clear. Now what we can write in common, that 3V plus IZS, but this is our 3 E naught I. E naught is our voltage induced across open circuit armature terminal with same level of excitation. So this is 3 E naught I. Now also what we can write, like another definition of I, we can write it like E naught minus V by ZS. Now this is all phasor. If you ask me to write it more clearly, I can write, considering V as reference, E naught delta minus V0 by ZS angle gamma is equal to E by ZS angle delta minus gamma minus V by ZS angle gamma, right? So let us again consider this dot product, right? So what we will get, PE is equal to 3V dot I, right? Now your, what about your um, like electromagnetic input power, PM, that if you calculate, it will come out 3 E naught I. So that will be, correct. Now see the beauty. As I have already mentioned, here I am not going to consider anything that is constant loss, because it is expected from the name that synchronous machine. And if you consider the constant losses, they are either depending on your frequency or means voltage. Although there is certain level of voltage regulation in salient synchronous machine, but in synchronous machine that level of regulation is not that high. Generally, if you means forget about what we calculated and means what are the some very means striking results we got during solving numerical problems, but in general we will not find any machine that is having a regulation value, very high value of regulation. Moreover, what is done, that if you recall, that even regulation value is high, that doesn't mean your induced EMF is affected to a great extent. Let me repeat what I am saying, that even your regulation value is very high, we are committed to maintain a certain level of voltage across our machine terminal. So, in case there is a drop in our output machine voltage, machine output voltage, we adjust the field current in such a extent that means when we get extremely high value of regulation, like near about 80%, in that case what happened, that we took a linear assumption and then we try to anticipate that had we applied this much current through our, or allowed flow of current through our field winding, and kept it kept our terminals open, based on linear assumptions, what would be the amount of voltage we would have would have induced across our machine terminals, open circuit machine terminals, and that gave us that 80% or whatever. But what actually governs your machine core loss, very important thing, it is the terminal voltage and frequency of the machine. Terminal voltage, if you deduct the proportional amount of armature circuit drop, that will give you a value of your induced, means V plus IR. More specifically saying, that is the amount of means induced EMF, and that is, or means hardly you could include V plus I R plus J I X L, not XS. XS is not a XS. XS is no way a physical one. So maximum E is your induced EMF. Now, if you consider the magnitude of E and V, they are most of the cases almost proportional. So, if you are keeping your V to a rated level, you can expect that for rated current also, E and V will be like there is not a very means deviation between E and V will be very small, means, or sorry, not deviation, rather difference between E and V will be very small. So in that case, what I am trying to means assert is that it will remain the if you are committed to keep your terminal voltage constant, your internal like constant losses comprising core loss will remain constant, because you cannot vary the speed of alteration, and thereby you are committed to uh, allow your machine to maintain constant frequency, and you are committed to maintain voltage. So basically you are committed to, or means rather your actions are ensuring a constant core loss. Now coming to your second part, that windage and other losses whatever we are having, they are mainly function of speed and machine operating condition. Now machine are generally so designed that their operating condition should not vary for their intended period of operation. Like if it is a 2 hour means the machine is designed for a 2 hour 3 hour operation, then it should not means it should be in equilibrium. That equilibrium should be reached very quickly, and thereafter the machine should not deviate from that equilibrium to a considerable amount if you ensure that you use that machine within that span. If you suppose a machine is designed for 2 hours and you are keep on continuously using it for 8 hours, then nobody can ensure that what is going to happen with that. That may lead you to some undesirable circumstances. But otherwise, you can ensure, means as a designer, every designer are committed to ensure that if you abide by their guidelines, then their machine should reach the equilibrium pretty quickly, and thereafter it should stay there. So what is the motive behind stating you all these stories is that you can understand that how the mechanical losses remain constant. Now, keeping to our problem here, uh, this gentleman, if we can ensure that what is R? R is the resistance in armature, loved value of resistance present in armature circuit. So if we ensure R tends to 0, that will imply your gamma tends to 90 degree, and thereafter you will see a very striking change in this, and also this will further imply so it will become, and this rest will vanish because cos gamma cos 90 is equal to 0. Similarly this term will vanish, right? Here this will become also sine delta. So that is pretty obvious because the only loss we are considering is the variable loss taking place, or ohmic loss, that is across our armature circuit resistance. So if we make armature circuit lossless, then it becomes this PM, the electromagnetic input power, is equal to your this much. So what we can draw is that we can draw our diagram. The diagram is same for cylindrical rotor machine and motor. Like this is the diagram. You should get a perfect sine wave. I am not able to drawing it, but you should get it a perfect sine wave. So uh, now what I am trying to say here is that, well, just let me share the picture from any book. So here, this is the good and properly drawn diagram. You can see that when our gamma is sine, so basically what we can write is that uh, let me write here. So this is the expression. Now you can see that this is based on neglecting ohmic drop or ohmic loss across armature resistance. So what we are getting here is that it's a, means if we consider here the first half, that is very interesting, that in this region when delta is varying from, then we will have sine delta greater than 0, right, in this region. So when this is maximum when delta is equal to 90 degree. Later on will show you that for stability it should be, delta should be selected even in generator operation, that value less than 90 degree, right? But in case of practical case, although your delta is equal to 90 degrees, the maximum value, generally considering all the stability limit, we can go at max this portion where delta is equal to 40 degree. This is the practical limit. Now, what is the physical interpretation of that delta? What is delta? Let us go back to phasor diagram once again. Here, you can see that delta is the angle between your E naught and your V. So, this is our E naught, that is the uh, like how we can interpret delta, like if we consider that delta, first of all try to understand that here we need to do a little modification because this gentleman R is no longer is considered here, so it will become something like this, where this is JIXL, this is JIXAS. Now delta is equal to 90 degree. It's a means you can understand that it's clearly a very hypothetical situation, because how it can become 90 degree. Think about it. Like your even if you consider that your IR is in phase with your V, still this will become this, and means delta is equal to 90 degree, isn't it? Like indicating a situation where you are having case where it e to the power 0 is considerably greater than V. Think about in terms of physical realization, that how you can reach that point. Moreover, that I means these are the two sides of the triangle now. So if you want this side to be 90 degree, so basically if consider a triangle where you have this kind of consideration, right? Now here if you want this guy to be delta is equal to 90 degree, this is V, huh? And this is your IXS. So one choice is that you make this E naught very high. Another choice is that you select a current, like if we select current like this, so reaching that value with lagging current implies a very high value of E naught. Now think about a leading current. Let me drop these guys at this moment, otherwise they will make you pretty complicated. So this is our V, this is our I. Now if this is the case, then we can have something like I must be okay, let me first draw JIXS. This is our clearly we are having a I that is like this. JIXS phasor should lead I by an angle 90 degree, and in that case, see, that is when you can have basically this guy. Oh God. And this gives you delta is equal to 90 degree. This is a physical case, means like while having finite V and E naught is allowing you, rather if you see that magnitude of E naught is smaller than V, because this is a capacitive case, leading current, the machine is connected with a capacitive load that is drawing leading current, and therefore you are having negative regulation. All these are good, all these are good, but now now think about, or means consider the magnitude of JIXS. See that like reaching here, if you see, now it is becoming a right angle triangle, and this JIXS is the hypotenuse of that right angle triangle. So do you have any idea that basically you are looking for a situation where IXS is root over E naught square plus V square. So what is the magnitude of IXS you required? Isn't it very, very high? So even if you are considering leading, lagging, is that, but still the value of I that you need to circulate through your capacitive load is so high, because excess you cannot change. For a given machine, excess is fixed, right? And if it is means ergonomically designed machine, then the excess should be kept within a band. So that means you are need to circulate a huge amount of current I, and in reality that is not no way possible. So that limit us to keep it within 40 means that like stability and all other consideration. If you keep on considering them one by one, stage by stage, you will find that in reality, if we can make 40-degree delta, that is our great achievement. So hope you understand it, and if you understand, then hopefully you will enjoy it. Let us go to salient pole case. Now let us consider the case of one thing I forgot to just discuss, that in case of motor, what happens? In case of motor, it is like this part. So you can see that now delta is 0 to like the negative part. And obvious, if you consider the motor phasor diagram, you will also see that in that case your E naught is actually lagging behind V. Means we can have two ways to express this. Like you could go beyond to 180 degree. In between 180 to 360 degree, you could get the same kind of negative lobe of sine wave. But here, that important thing is that why it is so from 180 to minus 180 rather than 0 to 360 degree is because like 0 is something where your E naught and V, they become collinear phasor, and then it is like we are trying to draw a conclusion, like where it is start from one end and then it goes to means yes, okay. Now let me explain that why it is 0 to 180 and not 0 to 360. Rather, if you consider, as I have already mentioned, that practical limit of delta is like this much. So also it becomes somewhat meaningless to reach this region practically in this way. Rather, it is a very like obvious choice that you are not able to go to that region, and therefore means what I am trying to say, in reality, if we consider the case actually is something like if we need to shade a band region, then this is the region which we can actually cover. The range of delta between which we can operate. Right. Now we can go to the case of salient pole machine. In case of salient pole machine, let me write. Let us begin with the same kind of things that we did, but Just let me quickly draw the phasor diagram. Oh God. For sake of simplicity, I'm just uh, means disregarding the R. So we are having this I, and thereafter we'll have I D and IQ. So let me draw ID and IQ. Now draw JIDXT. Just a minute. And this side is JIQXQ. So this angle is delta. This much is our beta. Now let us proceed. What we can write here is very important, that P will become 3V. Now here, instead of E, what we can have is that we have already seen it, that we'll have JIXQ. So it is like 3VE1. If you want, then you can write it like ZQ cos gamma minus delta minus 3V square ZQ cos gamma. I am considering this expression is considering R. So PM will be just like the previous case. Right, where your ZQ is equal to and gamma is equal to Correct. Well, so here, as we know that, like dwelling with this and like although it's giving us a impression quite alike of our previous one, but we know that here we have xt, xq, and somewhere they must be present. The reason behind my question that I asked a few days back, that what is the relation between beta and theta, I hope that you seriously figure it out once you watch this video completely. Obviously, I cannot take the responsibility if you watch any other video that might be misleading in some way, but otherwise I can try my best to make you understand from this video, or means if you watch it mindfully and means have something means like having normal ability to understand, then you will also get it. So once again, what we can write is that something in terms of open circuit. Uh, can't we write, try to understand this, I cos theta is equal to, check it, what is our I cos theta? I cos theta is projection on this. This is our line of I cos theta. Now see that isn't it is like IQ cos delta plus, since this angle is 90 minus delta, so this becomes id cos of 90 minus delta or id sine delta. So if we add these two, we'll get this one. So here we can write this. Now see that with this description, more importantly what we can write, like p is equal to 3v E naught, sorry, 3vi cos theta, that is our output power. So that is equal to 3v id sine delta plus 3v iq cos delta, right? Now here again, what we can write about id, id is equal to, see, this is our e naught. Now this length is how much? This is v. So this is, if we do e naught minus v cos delta, then that is equal to idxd. So we can write, as we know that xd is almost constant for a given machine for nominal operating condition, and iq is equal to, similarly, now if we neglect the loss, then what it would become? Pm is equal to Pe. This is very important line, try to understand. Will become 3ve naught uh, minus v cos delta by xd sine delta plus your 3v v square sine delta by x cube. Correct. Now, from this, what we can further write, like we will get PM is equal to PE is equal to 3V E naught XD sine delta plus 3V square by 2 1 upon x cube minus 1 upon xd sine 2 delta. So in case you are means operating in generating mode, in addition to this power you need to supply your 3 I square r and other losses from your prime mover. And in case you are dealing with motor, your like this torque will be generated and means after subtracting that from your input, your 3 I square r, you should get this amount of torque. See, here it is very interesting to note that what I am trying to say, that it's really very interesting. Unlike the previous case, here we are having something, this guy, an extra term. This is due to saliency of our rotor structure. And clearly, more we make it salient, like more the difference between xd and xq, this term will have a significant effect. So now what would be the plot? Let me show you. The plot would be something like this. So here you can see that this dash line, this one due to the saliency term having twice of angle delta, and this one is the first term. So gradually you are getting this kind of shape. So apparently for small value of delta, this machine can gives you more power, right? Now if we want to find out the maximum power angle, like previously it was a plain and simple sine wave, so it was quite easy for us, but here we need to do that a little bit calculation, like dp d delta is equal to 0. Since the curve is smooth, so we can do this dp d delta is equal to 0, and that will lead us to a case where v e naught by xd cos delta plus v square 1 upon x cube minus 1 upon xt cos 2 delta is equal to 0, which finally lead to a case delta is equal to cos inverse root under a square plus 8b square by 4b minus a, where a is, this term is our a and this term is our b. So this is all about the power. In our next video we'll discuss about like the means different type of circle diagram for a synchronous machine, and that is going to be very interesting, and then we'll discuss some problems of synchronous motor, and at the end we'll discuss parallel operation. Clear?